Alright, let's get started. Welcome to the very last chapter of the Calculus 2 class for engineering students. This is chapter 6, Differential Equations, as you can see in the title of this slide. My name is Monchai Kuekachai. I will be your instructor for this chapter. First, let's take a look at the table here. The idea of the very first slide is to tell you what is coming and to give you a kind of outline of what are we going to learn throughout this chapter. First, we will walk you through all the basics. What I mean by all the basics, I mean we are going to discuss on the definition of differential equations and then talk about some concept and terminologies. After that, we're gonna look at some form of differential equations that are easy to solve, including separable equation, homogeneous differential equations, exact differential equations. And then after that, we're gonna learn how to convert non-exact differential equation to exact differential equations by using integrating factors. And then we're gonna wrap up the chapter by looking at linear differential equation and Bernoulli differential equations. That's all the plan for this chapter. So now, let's start by the definition of a differential equation. So what is a differential equation? So by definition, a differential equation is an equation involving a function and its derivative. So I will give you example. Here's an example. Example number 1. Let's say that you have dy by dx equal to x squared plus sine y. So this is a differential equation because it shows you a relationship between x, y, and dy by dx. In this differential equation, you can interpret x as your independent variable and y as your dependent variable, right? And that will give you a function y equal to fx and its derivative is dy by dx. As long as you have an equation that shows a relationship between y equal to fx and its derivative, that thing is called a differential equation. Another example, maybe you have y triple prime plus sine x times y double prime minus 2xy prime plus 3x sine y equal to 0. This thing is also called a differential equation because it shows you a relationship between x, y, y prime, y double prime, and y triple prime. Well, maybe you're gonna see more complicated differential equation. Something like, let's say you have the second order derivative raised to the 5th power minus 4x times dy by dx square and then minus plus 10 equal to 0. This thing is a differential equation too. Well, let's make it more complicated. Maybe you're gonna see some partial derivative too. Sometimes you could see the second order partial derivative with respect to x2 times plus second order partial derivative with respect to y2 times equal to 0. Well, this is also called a differential equation too because it shows you a relationship between x, y, a function f(x, y), and also its partial derivative. So the next line that I have here, I said that differential equations are called partial differential equation, in short PDE, or ordinary differential equations, in short ODE, according to whether or not they contain partial derivatives. So the example of PDE is number 4 here. This is the example of PDE because it contains partial derivative. Actually, this thing is called heat equation. Well, some of you could see this thing in the future. But when you model heat equation, you're going to use this differential equation. And if the differential equation does not contain partial derivative, we just call it ODE, ordinary differential equations. The examples are number 1, number 2, and number 3. They are all ODEs. So let's talk about another terminology here, which is called order. The order of a differential equation is the order of the highest derivative present in the equation. So you have to look at the order of the highest derivative. So for example, in the equation number 1 here, this is differential equation with order 1 because the order of the highest derivative is 1. Here is dy by dx, right? And this is the first order derivative, so the order is 1. So for number 2, this is a differential equation with order 3 because the order of the highest derivative is 3. So you could see the third order derivative here, y triple prime. So for equation 3, the order is 2 because you have the second order derivative here. Some of you are confused with number 5 here. So number 5 here, this is not order. If you want to call this thing, this is called degree, not order. So equation number 3 here, this is a differential equation of order 2. But if you ask for degree, this is degree 5 or the 5th degree. Now you may have a question that why should I be interested in differential equation? Why should I care this stuff? So I have a short answer for you here. Actually in real world, you cannot model things by using just a simple equation with x and y. So for example, let me show you the graph of the stock market. For example, let's say that you work in the financial mathematics fields and then you want to capture the behavior of the stock market. So some stock may have a graph like this, right? You can see that it's go up and down, up and down, up and down, something like this. So you can see that this pattern or behavior is so hard to capture. How could you capture it? By using equations. For sure, if you just use x, y equal to x squared, y equal to x cubed, y equal to square root x, it seems impossible to capture this pattern or behavior. To make the model more realistic, you have to add something more into your equation. And the thing that you could add is the rate of change. As long as you want to add the rate of change, which is here, rate of which thing happens. So it means you add derivative into your equation. Once you add your derivative in your equation, that thing is called differential equations. There are so many fields that you're going to see differential equations. I list as an example here, fluid mechanics, circuit design, heat transfer, population biology, option trading, for example. And then you have so many fields that you can see differential equation in the future. Another question is, will I learn in this course how to solve all the differential equations that I will ever be interested in? The answer is no. In this class, what are we going to learn is we are going to learn only some easy form that you can solve it by hand. In reality, you may have to face a differential equation that you cannot solve by hand and you have to use computer to help you to solve it, or you may have to just approximate it by using numerical methods. Well, that is the real world. But to give you the idea of the differential equation and give you some strong background in the first order differential equation, we're gonna learn some form of differential equation in this class. And those forms you can solve by just using basic idea of calculus. Alright, next let's talk about solution of a differential equations. One thing that you have to keep in mind is a solution of a differential equation is a function. It is not a number. Let me give you an example here. Let's say that you have a differential equation y double prime plus 4y prime minus 5y equal to 0. If you have a differential equation like this, you can see that in order to solve this thing, you can view y as fx, right? And then this thing is equivalent to f double prime x plus 4f prime x. and then minus 5fx equal to 0. When you solve this differential equation, so what are you going to get? Your solution is going to be fx equal to something, right? Because you need a function fx that fit into this equation. You need a solution fx that if you take derivative 2 times and then plus 4 times take derivative 1 time minus 5 times that fx, and then it's go to 0. That is what you want. So you can see that solution for a differential equation is always a function, not just a number, compared to the world that you learn when you learn algebraic equation. Let's say that when you have algebraic equation, this is the one that you learned before. In real numbers, let's say that you have x squared plus 4x minus 5 equal to 0. You can solve this algebraic equation by just saying that, oh, this is going to be x plus 5 times x minus 1, and then you're going to have x equal to negative 5 and 1. Well, you can see that solution for algebraic equation, they are numbers, not a function. But when you solve for a differential equation, the solution, it's going to be functions. Well, let's take a look at example. So verify that the function y equal to c1 sine 4x plus c2 cosine 4x, where c1 and c2 are arbitrary constants, is a solution of the differential equation d square y by dx square plus 16y equal to 0. Alright, I have this function which is claimed to be a solution for this differential equations. So this differential equation is the same thing as y double prime plus 16y equal to 0. So what are we going to do is we are going to differentiate the given function y 2 times and then see if it match with the given differential equation. So I have y equal to c1 sine 4x plus c2 cosine 4x. Then I differentiate 1 time, so I get c1, this is constant. Differentiate sine 4x, I get 4. Differentiate sine, I get cosine. And then plus c2, differentiate cosine 4x, I get negative 4 sine 4x. Right? And then after that, I differentiate this thing another time. So okay, let's simplify first. So you get 4c1 times cosine 4x minus 4c2 times sine 4x. Now I differentiate one more time. So y double prime is 4c1 differentiate cosine 4x. I get 4 times negative sine 4x. Alright. And then minus 4c2, I differentiate sine, I get cosine 4x. Alright, simplify it. So I get negative 16 c1 sine 4x. Oops. I need a constant here too. This must be 4 cosine 4x. Right? This is going to be minus 16 c2 cosine 4x. Alright, that is y double prime. And then after that, well, let's check if it fits into differential equation here. So y double prime plus 16y equal to negative 16c1 sine 4x minus negative c2 cosine 4x. Right, plus 16 times c1 sine 4x, and then plus c2 cosine 4x. Well, and then you can group things. So negative c1 sine 4x cancel with 16 c1 sine 4x, and then negative c2 cosine 4x cancel with c2 16 times c2 cosine 4x. So it's cancel out, and then this thing is 0. So y equal to c1 sine 4x plus c2 cosine 4x is indeed a solution. Alright, that's how you complete example 1. You can see from this example that, well, the solution of a differential equation must be a function. Okay, now let's talk about another terminology in differential equation. So general solution versus specific solution. So what is a general solution? So a general solution is a solution of a differential equation that contains arbitrary constant. So by this I mean, as long as your solution contains unspecified constant, that thing is called a general solution. For example, let's say that you have dy by dx equal to x. Well, this thing is simple. And if you solve this differential equation, a general solution is y equal to x squared over 2 plus c. This is a general solution of differential equation dy by dx equal to x, right? You can see this is called a general solution because you have c here. This is the value that you have not specified. So the value of c can be anything. So this is still called a general solution because the solution is general. It is a family of solution. It can be y equal to x squared over 2 plus 1, y equal to x squared over 2 plus 2, y equal to x squared over 2 plus 3, and so on. C can be anything because it always match with the differential equation dy by dx equal to x, right? Does it make sense? Well, that thing is called a general solution. So to observe that thing, you can observe that it's always come with arbitrary constant, a general solution. For a specific solution, what is a specific solution? So in other words, a specific solution or particular solution, the same thing. So a specific solution is a solution that satisfies some additional requirement. So if you add some additional requirements into differential equations, so you can solve for c, solve for some constant, and that answer will be your particular solution. For example, let's say that I have dy by dx equal to x together with the condition, let's say the initial condition y1 equal to 3. So I have this thing. So I have dy by dx, and I also know that I have the initial condition y1 equal to 3. How do I solve this thing? So to solve this thing, you may get a general solution first. So a general solution is y equal to x squared over 2 plus c. This is a general solution. And then with the initial condition that you have, y1 equal to 3. This thing means when x equal to 1, y equal to 3. So it means if you plug in x equal to 1, you're going to get y equal to 3. And from that, you can solve for c. So this thing you're going to get 3 minus 1/2 equal to c, which is c equal to, let's think about it. It is 5 over 2, right? So that is the value of c. So once you solve for the value of c, then you plug in c back into the general solution. So to sum up, a particular solution or specific solution is y equal to x squared over 2 plus 5 over 2. This is a particular solution for the initial value problems dy by dx equal to x with the initial condition y1 equal to 3. Another terminology that I just introduced you is, once I have differential equation here together with the initial condition, we're gonna call this thing initial value problems. Initial value problems, or IVP. That is the standard notation that people use in the real world. So we're gonna stop it here, and then on next video I'm going to start showing you how to solve differential equations. Now you're gonna learn how to get the solution or a general solution of the differential equations. So let's start by the easiest case, which is going to be a separable equation.